Similarly, if I fix B, I get a contravariant. So where does this go? The representable functor goes from C into, so the functor looks like this, HOM, I better write bigger, right? So the representable functor of A, representable functor of A, I want to emphasize this, is HOM A blank. It goes from C into the category of sets. Right? It takes an object X to the set of all arrows from A to X, and it takes an arrow F to the function given by composition. That's a representable functor. And there's a contravariant representable functor, covariant. And just as in sets, there's a contravariant representable. This was fix A, now fix B. What I really mean is fix the first argument, fix the second argument, right? Fix B, and we get blank B. This is arrows into B, and it goes like this. It takes I'm just doing the set thing that I did before, but I'm doing it with these so-called HOM sets rather than with sets, X, B. That's a map, F upper star. It comes from a map going this way from X to Y, because this was maps from Y into B. So I take something here, and I precompose, and that gives me something over here. So this is the contravariant representable. Okay. These are really quite important, and you'll see later on what they're good for. Contravariant representable functor. So that's B. It's contravariant in the first argument, and so that's going from C up into set. Maybe that's all I need to say right now. So you have some homework exercises, and you'll get used to these representable functors. I think a homework exercise is to show, in fact, the whole thing HOM is a functor on the product category into set. And these are just its two parts. And later on, when we have a little bit more information, we're going to start looking at things of the form set to the C, the functor category, the objects of which are functors from C into set. The arrows we have to determine, those are called natural transformations. And then we'll see that, for example, we can have contravariant functors, and we can have C itself maps by this operation. It's basically the currying of this HOM functor, and that's an important map called the Yoneda embedding. So by the third lecture, we'll have the all-important Yoneda embedding. It's been said that category theory is really the theory of the Yoneda embedding. You can do lots of things with the Yoneda embedding. So we'll look at that later. Okay, that's it. Thanks. Homework exercises are on the web, so either go to the program web page. There's a link that says curriculum, I think. Yeah, and then there's a link to my lectures. If you go there, I've made a little page, and it's got some problem sets. The other way to find it, I think, is through my home page down at the bottom. There's a link to the summer school here, and then you go to that page, and then you've got the lecture notes and the problem sets. I'll be around to talk about the problems with you. There was a doodle poll where some people said that they're already quite advanced in category theory. So I know you're here. I don't know who you are, but there are at least 4 of you, I think, who said you already know some category theory. It'd be great. Maybe you want to raise your hands if you're confident about that. It would be great if you're around to help people too with questions that they might have about these exercises, because I didn't, unlike some of the other speakers, I didn't bring a student with me to act as a TA, so you can be my appointed teaching assistants if you want to do that. Maybe raise your hands a little higher so people know who to ask if you get stuck. These are your expert consultants, okay? Find the one nearest you, and that will be your person. Thanks.